space explorers and knowledge seekers, welcome back to another deep dive, where we unpack the universe's biggest topics for you. Today, we're heading right to the heart of our solar system, focusing on our star, the sun. It gives us life, but it's also, well, surprisingly dynamic.
That's right. And for this exploration, we've pulled together quite a range of sources. We've got insights from the Spanish Society of Astronomy, research articles via CLO,
Okay.
a really practical guide on sun protection from Esterafi, great info from NASA Science and Space Place, the trusty Wikipedia entries on the sun and solar wind, plus news on that big solar storm back in May 2024 from CSE, an article on storms from Casa de la Ciencia, and even a little peek into solar mythology.
Wow, quite the collection. So our mission today, folks, is to distill all that down. We want to pull out the most crucial, most fascinating bits about the sun's activity and its effects on Earth and beyond. We aim to give you a solid understanding, without getting totally lost in the weeds. Sound good?
Sounds like a plan.
All right, so let's start with the basics. The sun we see every day, it's not just a steady ball of fire, is it?
No, not at all. It's incredibly dynamic. And the main driver behind that is its magnetic activity.
Magnetic activity?
Yeah, and this activity follows a pretty regular cycle, roughly every 11 years.
11 years.
During that time, the sun's magnetic poles actually flip. North becomes south, south becomes north.
Whoa, okay.
And this whole magnetic cycle is what really influences the stuff we see on the surface, like sunspots.
Ah, sunspot. I've always wondered about those. What exactly are they, and why do they come and go with this cycle?
Right, so sunspots are areas on the sun's visible surface, the photosphere, that look dark because they're cooler than their surroundings.
Cooler, why?
It's down to intense magnetic fields. These fields essentially put the brakes on the heat rising up from the sun's interior in those specific spots.
I see.
And their numbers change dramatically over that 11-year cycle. We have what's called the solar minimum, where there are very few, maybe even zero spots. Then activity ramps up towards the solar maximum, and you see lots more sunspots. After that, it gradually winds down again. It's like the sun is breathing, in a way.
That's a great way to put it. Okay, now let's talk about something else flowing from the solar wind. Sounds like science fiction, but it's real, right?
Oh, very real.
Right.
A constant stream of plasma that's basically super hot, ionized gas, mostly charged particles like protons and electrons, and it flows outwards from the sun's upper atmosphere, the corona, at incredible speeds. We're talking supersonic speeds, hundreds of kilometers per second.
Wow.
Its existence was actually theorized back in 1958 by Eugene Parker, and space missions later confirmed he was right. Think of it like a constant cosmic spray coming off the sun.
Incredible. So the sun is constantly shedding particles into space. Does the solar wind have, a structure or different types?
It does, yeah. It's not just uniform. Firstly, it carries the sun's magnetic field out with it. And because the sun spins, this magnetic field gets twisted into a giant spiral shape.
Ah, like water from a rotating sprinkler.
Something like that. It's called the Parker spiral.
Yeah.
And we also distinguish between fast and slow solar wind.
Fast and slow.
Yeah. The fast wind comes from areas called coronal holes, usually near the sun's poles, and it zips along at maybe 700, 800 kilometers per second.
Okay.
The slow wind also comes from coronal holes, but more around the equator, and it travels at a more sedate 400 kilometers per second or so. Composition-wise, they're pretty similar, mostly hydrogen and helium ions.
Interesting, that speed difference based on where it comes from. Now, this leads us to something that causes both awe and a bit of worry. Solar storms. We heard a lot about that recent powerful one in May 2024. What are they and what can they do?
Right. Solar storms are essentially unusually powerful bursts of this solar wind. They get kicked off by more violent events on the sun, like solar flares, sudden flashes of radiation, and coronal mass ejections, or CMEs.
CMEs?
Yeah, those are massive eruptions, like giant bubbles of magnetized plasma being hurled out into space. And you're right, that May 2024 storm was a big one. According to CSE, it was the strongest we'd seen in about 35 years.
And the impact on Earth. We hear potentially serious warnings.
They can be very serious. When these intense bursts hit Earth's magnetic field, they cause geomagnetic storms. These storms can induce powerful electrical currents on the ground.
Currents on the ground.
Yes, they're called geomagnetically induced currents, or GICs. The real worry is that they can flow into power grids, overload systems, and potentially damage crucial components like large transformers.
Damaged transformers? That sounds bad.
It can be. We've seen it happen. The 1989 Quebec blackout was caused by this, and there was damage in South Africa during the Halloween storm of 2003. The potential economic losses from a truly massive storm could be, well, trillions of dollars, potentially causing outages lasting weeks or even months if many transformers are knocked out.
That's sobering. But doesn't Earth have some kind of protection, our magnetic field?
Absolutely. We have the magnetosphere. Think of it as an invisible magnetic shield surrounding our planet, deflecting most of that constant solar wind.
Okay, a shield.
Its size and shape are constantly adjusting, based on the pressure of the incoming solar wind pushing inwards and the Earth's own magnetic field and trapped plasma pushing outwards. During a solar storm, the wind pressure increases dramatically, and it compresses our magnetosphere.
So the shield can kind of get squashed, but it holds, mostly. What happens when some of that solar wind gets through?
Well, the interaction is complex. On the side facing the sun, there's a bow shock, like the wave in front of a boat. Behind that is a turbulent region called the magnetosheath. On the night side, the field gets stretched out into a long magnetotail. And importantly, particles from the solar wind can get trapped within the magnetosphere, particularly in the Van Allen radiation belts. These are donut-shaped regions full of high-energy particles spiraling along the magnetic field lines.
Got it. So it's this complex interaction, and that interaction when particles get channeled towards the poles, that's what gives us the auroras, right? The northern and southern lights.
Exactly. When those energetic particles, guided by the magnetic field lines, slam into the atoms and molecules in our upper atmosphere near the poles, they excite them. They give them energy. When the atoms and molecules calm down again, they release that energy as light. And that light is what we see as those incredible dancing curtains of the Aurora Borealis and Aurora Australis.
It's just beautiful.
And it's fascinating. NASA images show us that other planets with magnetic fields like Jupiter, Saturn, Uranus, they have auroras too.
Nature's light show across the solar system. Okay, let's shift gears a bit and look at the sun's whole life story. It formed billions of years ago. What's its future look like? How long will it stick around?
Well, the sun's been around for about 4.6 billion years. Yeah. It formed from the collapse of a giant molecular cloud. Right now, it's in its main sequence phase. That's the stable part of its life, where it's fusing hydrogen into helium in its core.
The stable part, how long does that last?
It's got about another 5 billion years left in this phase, give or take. But after it uses up most of the hydrogen fuel in its core, things start to change dramatically.
Dramatically how? I've heard about the red giant phase.
That's the one. When core hydrogen fusion stops, the core will contract and heat up. This will cause the sun's outer layers to expand enormously and cool down, turning it into a red giant.
How enormous?
So big, it's expected to swallow Mercury and Venus, and quite possibly Earth as well.
Whoa. Engulf the Earth.
It's a strong possibility. After that, the core will get hot enough to start fusing helium into carbon and oxygen. The sun will go through some other stages, eventually shedding its outer layers to form a beautiful planetary nebula.
And what's left behind?
What remains will be a white dwarf, a very dense, hot remnant about the size of Earth that will just slowly cool down over trillions of years, eventually becoming a cold, dark, black dwarf. Importantly, the sun isn't massive enough to explode as a supernova.
A relatively quiet end, then. But for life on Earth, how does this long-term evolution affect us before the red giant phase?
Well, even before it becomes a red giant, the sun is gradually getting brighter, about 1% brighter every 100 million years.
Doesn't sound like much.
It adds up. Over about 1 billion years, that increasing brightness will likely heat Earth enough to evaporate all our liquid water. Long before the sun engulfs us, Earth will become uninhabitable for complex life as we know it.
1 billion years.
Yeah.
Still a long time, but inevitable.
Yes. And it's interesting, as the Spanish Society of Astronomy sources point out, to contrast that long-term cosmic fate with the much more immediate challenges we face from human-induced climate change right now.
Definitely puts things in perspective, but you mentioned those sources also hinted at a sort of second chance for life far in the future.
Ah, yes, that's a more speculative idea. It explores whether life could potentially arise or persist around white dwarf stars, the remnants left after stars like our sun die.
Life around a white dwarf.
It's hypothetical, but planets would need to orbit very close to the faint white dwarf to stay warm enough. There's even speculation about whether microorganisms could survive the turbulent end stages of a star and maybe even get transported between systems. It's really pushing the boundaries of astrobiology, thinking about where life might find a foothold.
Absolutely fascinating, even if it's way out there. Okay, let's bring it back to Earth, back to the here and now. A very practical concern. Protecting ourselves from the sun's radiation today.
That Espiral guide had some key advice.
Yes, absolutely crucial. The sun's ultraviolet, or UV, radiation is what we need to be mindful of. While some UV helps our bodies make vitamin D, too much is harmful.
Harmful how?
Well, there are different types. UVC is mostly blocked by the ozone layer, thankfully. UVB is the main culprit for sunburn and plays a big role in skin cancer risk. Then there's UVA, which penetrates deeper into the skin, contributes to premature aging, wrinkles, age spots, and also increases long-term cancer risk. UVA can even pass through window glass. And even visible light can cause some pigmentation issues. So unprotected sun exposure is definitely risky for our skin health. What are the best ways to protect ourselves?
Prevention is key. The standard advice is really solid. Avoid the sun during peak hours, usually mid-morning to late afternoon when UV is strongest. Wear protective clothing, long sleeves, hats with wide brims. Good sunglasses are essential for your eyes.
Right.
And of course, use sunscreen, consistently, generously, on all exposed skin. Even on cloudy days, because clouds don't block all UV rays, and apply it year-round.
Sunscreen. There are so many types. Can you break down the difference between mineral and chemical sunscreens?
Sure. There are basically two main types of UV filters. Mineral filters, sometimes called physical filters, contain ingredients like zinc oxide and titanium dioxide. They work primarily by creating a physical barrier on the skin that absorbs most UV, around 95%, and reflects and scatters a small amount away.
Yeah, physical block.
Exactly. They tend to be good for sensitive skin, less likely to cause allergic reactions, and generally considered better for the environment, especially marine life, as they're biodegradable. Plus, they work immediately upon application and are quite stable in sunlight.
And the other type, chemical filters.
Right. Chemical or organic filters work differently. They absorb UV radiation and convert it into a small amount of heat, which is then released from the skin. They often feel lighter on the scare, but need about 20-30 minutes after application to become fully effective.
I see. Are there any ingredients we should look out for or maybe avoid in chemical sunscreens?
Well, some concerns have been raised about certain chemical filters like homosalate, octesalate, oxybenzone, and octinoxate. Studies have suggested potential links to endocrine disruption or environmental harm, particularly to coral reefs.
Right, I've heard about the coral reef issue.
Yeah. Because of this, many dermatologists and environmental groups often lean towards recommending mineral sunscreens, especially for children, babies, and people with sensitive skin.
Good to know. And what about SPF, that number on the bottle?
SPF stands for Sun Protection Factor. It merely tells you the level of protection against UVB radiation, the kind that causes sunburn. It's crucial to use a broad-spectrum sunscreen that protects against both UVA and UVB. And remember, SPF ratings are based on applying a generous amount. Most people don't apply enough.
Right, gotta slather it on. And apply even indoors near windows, you mentioned.
Yes, because UVA rays penetrate glass. So if you work near a sunny window or spend a lot of time driving, sunscreen is still a good idea. And after sun exposure, using an after-sun product can help hydrate and soothe the skin.
Very practical advice, thanks. Finally, just to round things out culturally, the sun hasn't just been a scientific subject, it's been hugely important in human culture and mythology forever, hasn't it?
Oh, absolutely. Across countless civilizations, the sun has been revered, often as a primary deity. Think of Ra in ancient Egypt, or Helios in Greek mythology.
And the sources mention Japanese mythology.
Yes. Amaterasu Omikami, the sun goddess, is central to the Shinto religion in Japan. The sun's power, its life-giving warmth, its daily journey, it's deeply embedded in our collective human story, even showing up constantly in modern music, as the NASA source noted, in lyrics across all genres and languages. It's a powerful symbol.
From ancient goddesses to pop songs, the sun's influence is everywhere. Okay, Cosmic Explorers, that brings us towards the end of today's deep dive.
So to quickly recap, we've looked at the sun's dynamic nature, its 11-year cycle, the solar wind constantly flowing out. We've touched on solar storms and their potential impact on our technology.
Right.
We explored the science behind the beautiful auroras, peered into the sun's very long-term future life cycle, and covered the vital importance of protecting ourselves from its radiation right now.
And that leaves us with a final thought for you to ponder. Given the immense power of our star and how increasingly reliant our civilization is on fragile technology, are we truly prepared for the sun's more dramatic moods? Are we doing enough to understand and mitigate the risks of space weather?
Definitely something worth thinking about.
We hope you enjoyed this journey into the sun. Let us know what you found most interesting or any questions you still have in the comments below. We do read them. If you found this deep dive helpful, please give us a like, subscribe to the channel for more explorations like this, and hit that notification bell so you don't miss our next adventure together. Thanks for listening.